Hi everyone and welcome to my talk, Deterministic Machine Learning with MLflow and mlf-core. Very briefly about me, so I'm Lukas Holmos and I'm based in Tübingen, where I've also received my bioinformatics master's from the University of Tübingen, and I'm a research software engineer at the Quantitative Biology Center in Tübingen. And one of the things that I particularly focus at with my research is reproducible research. Very briefly about the Quantitative Biology Center, or QBIC for short. So we are a bioinformatics core facility at the University of Tübingen, where we primarily conduct data management and data analysis for our customers, usually in the biology area. And we are a strong contributor to reproducible research, where we basically develop tools and workflows for reproducible research. We also have a job opening for a scientific data steward, that you can access via the shown QR code, but you can always reach me via your preferred means. I'm sure that most of you have already come across one of these headlines. For example, machine learning is creating a crisis in science, or artificial intelligence faces reproducibility crisis. But why do we actually care about these issues? So from a scientist's perspective, we base our work on hypotheses and we have to verify our hypothesis, because if we don't do so, then our next hypothesis that we basically put up might be based on completely wrong results and therefore just lead to even further wrong results. A few researchers evaluated reproducibility in machine learning. So they took a look at 400 papers and they found that only 24% of them were actually reproducible, quite a low number. Furthermore, we need to be able to audit machine learning models. So machine learning is now used in all kinds of sensitive application areas, such as terrorism detection or in health, and the public needs to be able to audit those models to actually verify that they do what they are supposed to do. Now, from a developer's perspective, we conduct a lot of experiments with our models and our code, and our models need to be deterministic, because if we don't know whether what we currently observe is due to our experimental setting or due to random factors, then we can't experiment at all. Furthermore, when we are actually debugging our models, we need to pin the origin of that error tightly, but we can't do so if we don't know whether our different model performance is due to randomness or due to the bug that we're actually trying to track. And finally, if we want to ensure that our model still performs as it's supposed to do, for example, when we add additional data, then we need to be able to form regression tests. And they can only really tightly verify that our model is doing what it's supposed to do when it's deterministic. But what are the primary reasons for non-reproducible machine learning? The first and foremost primary reason is that the data and the code is not shared. This was also found in the paper that I've just mentioned. Secondly, the documentation is oftentimes insufficient. So the hyperparameters, the metrics, and all kinds of numbers are not reported. Furthermore, the used hardware is very oftentimes not reported at all. But also, machine learning is oftentimes conducted in a irreproducible environment. So people use different kinds of versions for their libraries, and then this just leads to conflicts and completely irreproducible results. Finally, especially today, the usage of GPUs is really widespread due to the performance gain that they provide us with. But GPUs usually use non-deterministic operations and non-deterministic algorithms. So what could that actually look like? What you can see here on the slide on the left is a depiction of the so-called sum-reduce algorithm, which is based on CUDA, the underlying implementation or the underlying API that NVIDIA provides for its GPUs. Now, if you focus on the left, you can see if you start at the very top, you're always just adding numbers in pairs. For example, you add the 57 and the 19 first, and you get 76. Then you add the 52 and the 14 and you get 66, and you just continue this. Now, if you go to the next row, all you do is you add up two numbers. So what we're trying to do here is we have a lot of numbers and we want to add them all up to get the full sum. the sum reduce algorithm. The issue here is that those GPUs that we are using to calculate those sums, they operate in parallel. And actually summing all of that up requires synchronization. But when we make the problem more difficult and now turn our eyes to floating point numbers, then things start to get weird. Now here you have two experimental runs basically. We are calculating the sum twice using the same numbers. If you look on the left, the first thing that we do is we add the 0.1 and the 0.2, and we end up with 0.3 something. And next we add the 0.3 and we obtain some number, for example here 0.6, a lot of zeros and a 9. So it's not perfectly precise. There's some imprecision here. Now if we actually switch up the order and calculate the sum of 0.2 and 0.3 first, this time we end up with 0.49 and many repetitions of the 9 and then an 8. And if we then add the 0.1, suddenly we get a completely different number. So 0.59 something. Now why is that? Well, that's because the summation is not associative. But if we're doing that with GPUs, the primary issue here is that the order of the thread synchronization is always different. And this leads to different floating point errors. You can imagine that if you apply that algorithm many thousands or millions or even billion times, those very small errors that you can observe here, they actually add up. Yeah, and most machine learning algorithms, they are based on these atomic operations. But even though we've just talked about this issue, there are many more reasons for non-deterministic behavior, but this is the most prominent one that people are usually not aware of. But there have been some recent developments. So for the major machine learning frameworks such as PyTorch and TensorFlow, but also XGBoost, there are now actually deterministic algorithms and variants offered. And they are implemented without these atomic operations that I've just mentioned. But there's a couple of questions that we can ask. So are those deterministic algorithms actually working as expected? Are there options for all the algorithms available or only for a subset for them? And what is the effect on the runtime actually? Therefore, the first thing that I evaluated here are these questions, the following setting. So I have two basically containerized projects that are running in Docker and Singularity containers, PyTorch, TensorFlow, and XGBoost. The PyTorch and TensorFlow settings, they are basically trying to classify handwritten digits that you can see in the top right, the left image, from 0 to 9. And in the XGBoost case, I was working with the cover type dataset where we actually try to classify tree cover types into different classes. So this was kind of the aim of those settings. And I used three different systems to have different hardware sets to tackle the hypothesis whether the hardware has any effect on the determinism. So system one, which was just my personal laptop, had an i5 and a NVIDIA 1050M. The second system was a 12-core Intel system and had two NVIDIA Tesla K80s. And the third and the fourth system was a little bit more recent. It had 24 cores and two NVIDIA Tesla V100s. So when I was evaluating the determinism of these projects, I had three settings that I wanted to evaluate for the CPU and a single GPU and even multiple GPUs. So for each one of those three, I was running the experiments with no random seeds set at all. It's basically our basis hypothesis. Then with all possible random seeds set, and then with the deterministic algorithms that I just mentioned enabled, and with all random seeds set. And I was basically running those settings 5 times per setting. In the following, we will only look at the PyTorch results due to the interest of time, but the TensorFlow and XGBoost results basically tell a similar story. So what you can see here is a box plot of the PyTorch run with system 1, so basically my laptop. And what we're plotting here is the setting against the loss on the y-axis. So let's start from the very left. If we have the setting, system 1 on the CPU with no seeds set at all, you can see some variance. So it's not a flat line, but it's a box plot that actually, has a body. So there's some variation, which we don't want to have. Now, if you focus on the second setting, we suddenly enable the random seeds and we get a deterministic result. If we enable even further deterministic settings, there's not any effect on that. We still get deterministic results, which is what we want to have. Now, if you suddenly start using the GPUs, which is the fourth plot, and you don't set any seeds at all, you have a non-deterministic result. And now things get more tricky, and basically this demonstrates the issue that I mentioned earlier. If you now fix all of the random seeds, basically every seed that you can find, then you still get some variation and don't have a deterministic result. But finally, if we enable the deterministic algorithms, then yes, we do get a deterministic result, which is what we wanted to obtain. But let's switch hardware for a moment. This time we're doing the same thing, but with system 2, which actually has not a single GPU, but 2 GPUs, which allows us to test the same hypothesis for multiple GPUs. Now, the first 3 box plots basically resemble the story that I mentioned earlier for the CPU. Okay, if we enable all of the random seeds and enable the deterministic algorithms, then yes, things are deterministic. But things get more interesting when we use GPUs. So if you focus on the 5th plot now, basically in the middle, if you run your model now with a single GPU and with only the random seeds enabled, we suddenly have a deterministic result. Now, this is not what we expected, because in the plot earlier that I've just shown you, I've told you, okay, if you only enable the random seeds for GPUs, then you don't necessarily get a deterministic result. So why could that be? One reason that this could be attributed to is that the underlying neural network implementation that NVIDIA provides, which is basically called cuDNN, it has a benchmark setting. And this benchmark setting always tries to find the fastest algorithm for a given hardware. And I expect that in this case, it basically selected the algorithms which operate deterministically, and therefore we obtain this result. But you cannot always bet on that. So yeah, there's a guarantee, and therefore you can still enable the deterministic settings, which is the 6th figure here, and then you do always get the deterministic results, but they differ here. If you disable the deterministic results and only run the model with all random seeds set. The same story can in this case be observed if we do it with multiple GPUs, which are the 3 plots on the right. One thing that you should know is that as long as you keep the hardware consistent, so if you use the same hardware architecture, then you should always get the absolute same results given all deterministic settings are enabled. So in this plot, you can basically see system 3 and system 4, which were different systems but had the same hardware, and all the deterministic settings were always enabled. So the first 2 box plots are for the CPU, same hardware, deterministic settings, same results. Same story for a single GPU, and the same story for multiple GPUs. Maybe you noticed earlier that when we compared system 1 and system 2, that even if you enable all of the deterministic settings, the results are actually not quite the same. They differ a little bit. So what can we take from that? If you now evaluate the runtime, so should we enable those settings always or not at all? Because you can imagine that there's a reason why NVIDIA implemented those atomic operations. They are basically the fastest way to calculate a sum. So what is the effect on the runtime? If you just compare the GPUs here, which is what is shown in this plot. You can see the three box plots on the very left, which are the single GPU. And the third one, so the green one, is the one that we care about the most, because this is the one that has the deterministic settings enabled. And in this case, for only 5 runs, keep that in mind, the runtime was even lower than when we only had our random seeds set. So really there was no effect on the runtime at all. The same story for the next 3 plots, the next 3 figures here. If we take a look at the multi-GPU setting, then in this case, the runtime was a little bit higher than when only all seeds were set, but it was lower when no seeds were set at all. So basically, in the case of PyTorch, there really there's no reason not to turn these settings on because there is no real observable effect on the runtime. What are the primary takeaways from the experiments that I conducted? So first of all, we've discussed PyTorch, but I've mentioned it. Similar results were obtained for TensorFlow, but also for XGBoost. So those deterministic algorithms, they do work, but they are surprisingly badly tested. So during my evaluation, I found several bugs and I reported them and got them fixed together with the library developers. But still, I'm sure that there are many more issues that are actually hidden somewhere. And those deterministic settings, they need to be forced because sometimes the underlying implementation, for example, by cuDNN, will choose algorithms that might sometimes appear to be deterministic, but they might not always be. Furthermore, not every algorithm actually has a deterministic option. So some of the algorithms should not be used at all if determinism is of concern. And it's very difficult to actually get complete lists. So PyTorch, for example, mentions that they expect to have about 150 functions that are not deterministic, but they don't provide you with a full list. And therefore, it's even harder to actually keep track of those functions in your code because, as usual, you're writing a lot of code and you can't keep track of which of the functions you're allowed to use and which ones you're not allowed to use. Furthermore, determinism is actually hardware architecture dependent. So if you train your model on 2 completely different hardware sets, then don't expect to get the same results even if you have all determinism settings enabled. Also, what we've just seen, there is really a neglectable effect on the runtime. So Duncan Reich from NVIDIA, he conducted even more experiments that I did on a far more larger model. And according to him, for TensorFlow, there's about a 6% performance decrease if you enable all of the deterministic algorithms. I personally consider this to be fine because you're saving a lot of time with determinism. And yeah, you can really speed up your experimentation. So it pays off, I think. In summary, what are the requirements for deterministic machine learning? So based on the experiments that I've conducted, we should keep track of all of the hyperparameters and the metrics that we actually obtain and document our model in depth. Furthermore, we should also run our model in a reproducible container so that we can ensure that we always use the absolute same runtime library versions. And thirdly, we should always enable all of those determinism settings for the machine learning libraries. And finally, we should keep track of the hardware that we actually use, because if we switch to different hardware, we also won't get a reproducible result. So if we adhere to all of those requirements, then we should get reproducible runs and always the absolute same result. But these are really complex requirements. There's a lot that you as a developer have to keep track of. So what we actually need here is an intuitive software solution. The solution that I will now present is based on MLflow by Databricks. And the primary 3 components that we are making use of is, first of all, the tracking component of MLflow, which allows us to record and query our experiments. It allows us to keep track of our hyperparameters that we're using, for the metrics that we obtain, and these kind of things. Secondly, we will make use of MLflow projects, which allows us to package our code and our project the reproducible format that we can then run on any platform. And thirdly, MLflow models allows us to really deploy our model in an easy manner and keep track of all of the models that we've trained. So based on MLflow, I would like to introduce to you mlf-core, which is inspired by the mlf-core projects, and it's really designed to enable deterministic machine learning. Just a small overview. What does MLflow actually give you? So mlf-core provides a super easy way to create projects based on project templates. And these project templates, they actually are already deterministic from the get-go. So you start with a CPU and GPU deterministic project template. Secondly, those templates come with a super rich continuous integration pipeline. So for example, a Docker container is built right from the beginning for the project. There are various code linters. So linters are tools that statically analyze the code that are running from the get-go. Your project trains on a small training subset to verify that it's always working, these kind of things. Thirdly, mlf-core implements a custom linter. Now this linter we will discuss a little bit later again, but this linter will statically analyze the code to verify that it adheres to all of the mlf-core standards. And of course, as you can imagine, one of the mlf-core standards is that your code, your model, is always deterministic at any time. Furthermore, mlf-core has a so-called sync feature. So we from MLf-core, we will always improve the MLf-core templates. But if you created a project, say 2 years ago, and we are releasing a new version of MLf-core with an updated template, for example, for the PyTorch template that you used 2 years ago, then you will automatically get a pull request with only the changes that we've made to that template. This ensures that you're always up to date, that you always use the most recent MLf-core standards to standardize your project and to really ensure that it will always be deterministic. Furthermore, MLf-core is well documented and you will find a lot of help in documentation to get started, but also to use some of the more advanced features. And finally, we're trying to build a community around MLf-core because deterministic machine learning and reproducible science are really important to us. We want to ensure that even in the future, when things will change, MLf-core will always be able to provide deterministic templates for you. What are these available project templates? So at the moment, we have 4 project templates in MLf-core. So the first one is a PyTorch template. The second one is a TensorFlow template. And the third one is a XGBoost based template. And the fourth one basically combines XGBoost together with Dask, which is kind of comparable to Apache Spark, but more used in the Python community. And this allows you to use an XGBoost to train an XGBoost model on multiple GPUs even, which is not supported out of the box for XGBoost. Now let's take a look at a small GIF that basically demonstrates the process of creating an MLf-core project. Let's start from the beginning. There we go. So first you will be asked for the primary framework that you want to use. In this case, we selected PyTorch. We enter a project name and we enter a project short description. Then we select the current version, a license, and whether or not we want to create a GitHub repository automatically. Now, if we do so, if we want to create a GitHub repository, then it will automatically create one for us, even for organizations or for private repositories, and will automatically upload our project code from that template to that repository. And now this huge kind of colorful blob that you can see here is the MLf-core linting running once, which will verify that the project that you've just created does actually adhere to all of the standards. We will take a look at that later in more detail. But this is just to give you kind of an impression. This is super easy and intuitive, and you have just basically have to enter a few things and select things with the arrow keys. Super intuitive, and you end up with a complete project. So what you get is this setup here. So a lot of files that we really can't discuss in detail, but yeah, it comes with a full GitHub Actions setup with an MLflow setup, a Conda setup, Docker setup, and treated docs, and yeah, a lot to get started with. Now, if you train one of those models with MLflow, you can see here that yeah, it basically gives you the starting time of the parameters that your models was trained with, all of the metrics. So this is all logged for you. Secondly, if you train one of those models, you get a few additional reports besides the model that I usually keep track of. So you get a system intelligence report that shows all the GPUs that you've basically used. So the hyperparameter tracking and the GPU tracking here that you have for system intelligence tracks the complete hardware for you. So this solves kind of the tracking problem that we talked about earlier. Now, if you run mlf-core lint manually, basically what you end up with this. It runs a whole bunch of tests, for example, for the versions that your project has used. Are they still up to date? Yeah. Or do you need to update them? Are there any to-do strings left? And at the very bottom, I want you to focus on that. You can see some test failures in this case. So it will tell you if you use any of the non-deterministic algorithms, or if you deleted any of the required seeds, and will make you aware of that. But you, as a user, you don't need to be aware of all of those issues, because mlf-core lint will basically tell you on what you need to fix in order to make your project deterministic. This solves the requirement for the deterministic settings. Now, to bring it all together, MLflow together with reproducibility solves the documentation issue. Conda together with Docker solves the container issue. And finally, mlf-core ensures that you're always using the deterministic algorithm settings, but also keeps track of the hardware. Therefore, we get reproducible machine learning. You can go even one step further from MLflow together with mlf-core and basically create PyPy and Conda packages from that. And you can then integrate them into more complex pipeline setups such as Nextflow or Airflow. So really whatever you want. Therefore, get deterministic end-to-end pipelines. Further work, what are we going to do? So we will be trying to add more templates for even more machine learning libraries that are supported in MLflow. We will try to provide templates that basically give you a simple way to create Python packages to integrate them into more complex pipelines. We will be working on improving existing templates to provide even cloud configurations, hyperparameter optimization, and these kind of things. And we will also try to add a couple of more advanced example MLf-core projects for popular architectures, for example, for a GAN or for variation autoencoder, these kind of things for reference implementations. And therefore, we would like to invite you to join MLf-core. So it's on PyPy, just installed with pip install MLf-core license under the Apache 2 license. Furthermore, join our Discord if you want to ask any questions about deterministic machine learning in general or the MLf-core package. Contribute to the code if you want to on GitHub, and take a look at our website on mlfcore.com. Finally, just a few acknowledgements. And I would like to thank Sven Nansen, Philip Hennig, and Gisela Cabernet, who were the supervisors for my master thesis, on which this is based on. Duncan Reich from NVIDIA for a lot of helpful comments, the mlf-core project for inspiration, and the Denby Cloud for providing me with the machines to run those experiments on. Thank you very much.